Testing. Okay, I think we shall begin. Welcome to DSC NUS Workshop 4, Machine Learning and Analytics. So for those who are first-timers, the following are the links that you can receive our workshop materials. We did basic Python, followed by data collection, data visualization, and workshop 4 is on machine learning. So welcome to our workshop series. Introducing our team, we have Melodies, who is our tech lead, Evan, our deputy tech lead. And this is us. I am Jet. Jing Yang will be presenting for the next half. We have Michael and Ita. So what we'll be covering today is machine learning algorithms, specifically regression, classification, linear regression, logistic regression for classification, as well as clustering, specifically k-means clustering. We also do model evaluation, such as train, test, split, shuffling of the dataset, and certain metrics to evaluate your model's performance, such as accuracy, confusion matrix, precision, and recall. So, machine learning. What is machine learning? Machine learning is the study of algorithms, statistical models that computer systems use to perform a specific task without using explicit instructions, relying on patterns and inference on the data. So traditional programming is that given an input, the programmer, creates a set of rules to program out a script and then convert the input into output. In machine learning, what we have is the data, the input and the output, and what we want to do is automate the approximation, the function approximation, so that we know the mapping from input to output. So what we'll be doing today is linear regression, logistic regression, and k-means clustering. So before I begin, may I know, just type in the comments if you guys know what is the difference between supervised learning, unsupervised learning. Yeah, the difference between the two. Yeah, just give it a few seconds. Just type in the comments if you have heard of the term before. So linear regression is the first diagram here at the left. Logistic regression is the center one, and k-means clustering is the third one. So linear regression and logistic regression are supervised algorithms, supervised learning algorithms, while k-means clustering is an unsupervised learning algorithm. So what that means is, for supervised learning, we have both the data, the data features, as well as the labels. So labels are referring to the output that we want the model to predict from the inputs. So supervised learning, we have both input and output. For unsupervised learning, we only have the input, the raw data. We don't have any labels to tell us, for example, in this case, k-means clustering is a clustering algorithm. Given a set of points, what are the clusters that form from these points? So for example, it could be t-shirt size, say, let's say the green one is referring to size S, blue is referring to size M, and red is referring to size L. So the data we have is customers, say, heights and width. So from these continuous variables, we have a spectrum of lengths, right? So what k-means clustering is observe clusters where the density is the highest, and then label them as a cluster so that we can have a better one size match the cluster. So we have one specific size for size S that caters to all the sizes, body sizes inside the green zone, and M for the blue and red for L for the red. So that is unsupervised learning. We don't have the labels. We don't know whether the points belong to small, medium or large. What we have is just the input data. For supervised learning, we have the input, which in this case is the X, ranging from -20 to 60, and we have also the output as the training data, which is the Y. So given the set of X, we want to predict the Y. So this is a classic regression task. For logistic regression, it's regression, but we are going to use this logistic regression as a classification task. So what is the difference between regression and classification? Regression is the output that we want to predict is a continuous variable, while for logistic regression, we want the output to be a binary output, so either 1 or 0. So in this case, to make things simple, we will set the threshold to be 0.5. So say X is, let's say X is very big, it will tend towards the Y value of 1. So if it is 0.5 and above, we will just output 1. And if it's less than 0.5, we'll output 0. So this can let us perform classification tasks, whether something, for example, if the classification task is to predict whether an image is a cat or not a cat, and then 1 will be cat, less than 0.5 will be marked as 0. These are not cat. Yep, so these are the 3 machine learning algorithms that we'll be covering today. So linear regression. So here is a linear regression plot. There's quite a lot of things going on in the graph, which we will cover step by step. So linear regression is a linear approach to modeling the relationship between a dependent variable, the X, and one or more independent variables, the Y. Independent variables is the X and the dependent variables is the Y. So Y regression, we want to model continuous variables such as predicting the price of a house from its attributes, for example, the size. So size will be X, the price of a house will be Y. Sorry. So here, the linear regression equation is basically Y equals mx plus b0, which stands for the bias. It's just a linear model. M refers to the gradient, b0 refers to the y-intercept. So linear regression essentially is we want to create a best fit line. But how do we know whether the line is a best fit line? So with that, we introduce something called the error function or the cost function. This is mean squared error. So what this is that, so given x, we have a range of y's given by the blue line. The prediction of the model lies on the blue line, while the actual data points are the black dots over here. So when we look at the difference between the prediction, which are the dots on the blue line, versus the actual data points, which are the black ones, we can see the error term, the lines in red. So these red lines are all the errors that are the errors of our model as compared to the training data set. So what we want to do is we want to take the difference. So here yi is referring to the y value, the data set's y value. So that the when I is 1 is referring to the first point, when I is 2 is referring to the second point, and so on. This y, I'll call it y hat, is referring to the prediction, which are the points on the blue line. So this is called mean squared error. We want to square the error, and then we find the mean of it. Yeah, so how do we know whether a linear regression model is the best fit line? You can share in the comments how what should we do to make sure that the linear regression line is best fit? Okay, so what we want to do is minimize the error. So when the mean squared error is at the minimum, the line is of best fit. Okay, so let's go on. So how do we make the cost at its minimum? So here we will need gradient descent. I'm not sure whether you guys have heard of gradient descent. It is an optimization algorithm for finding the local minimum. In this case, what we want to do is minimize the mean squared error. So the mean squared error, as we change the values of m as well as the values of b0, the bias, the error term will change as well. So you can visualize it as a 2D graph. 2D, so we have an x, y, and a z. Let's say the z-axis is referring to the costs. Okay, try to imagine this a bit. For the x-axis, that would be m, the gradient. So we have an axis of m's, we have an axis of b0s, and we have an axis for the error. So when we plot this error on according to different values of m and b0, we get something like a quadratic curve in 3D. So how do we know when it is at the minimum when it's a quadratic curve? So we want to get when gradient is equals to 0. So we need the gradient. How do we get the gradient from a cost function? We will need to differentiate it. So this y hat is equals to this mx plus b0. This is our model. This is actually referring to y hat. Y hat equals to mx plus b0. So when we substitute inside this, we'll get y minus mx plus b0 square and then the mean. So if we differentiate it, we will get this y I minus mx I plus c. So c was the b0, right, bias, but let's just use c as the y-intercept. 2 is from when you differentiate, and then the square becomes at the bottom, and then the minus x is from here. 1 over n remains, and so on. So so these two are the same thing. So we want to compute the partial derivative of the loss function with respect to m. So m is our gradient, which is a parameter that we can change. We also want to compute the partial derivative of the loss function with this is c, with respect to c. So these are your gradients of your loss function derivatives. After that, after we have computed the partial derivatives, we want to update the values of m and c. So we want to change the values of m and c such that it minimizes the cost. So here is an intuition of how it looks like as we run this algorithm iteratively. So if you see from this animation over here, at iteration 0 it was not very fit. The red line is not very fit, but as the algorithm iterates, the loss minimizes, and then it tends towards the best fit line with the minimum cost. Okay, so let us go into the demo now. So go to the walkthrough, and I'll take you step by step through linear regression and gradient descent from scratch. Yeah. So when you are here, there should be I think you can't edit directly from here. You have to create a copy. So file, save a copy in Drive or something like that. If you have any problems, you feel free to comment on the comment section. Yeah, unfortunately due to COVID, we have to put this on live stream, but we have our full team here at the comment section to assist you with any questions that you may have. So feel free to make good use of their assistance. Okay, so linear regression. Okay, so here are the libraries that we'll use: NumPy, Pandas, and Matplotlib. This is a little trick you can use, which is to use the Seaborn style, and then all your graphs will look nice. Okay, but anyway, this is our linear regression model. It is a function which takes in a gradient, the list of input values, as well as the y-intercept. So I'm just gonna refer to my answer here and let's go step by step. So let's return a list of m times x plus c for x in x. So what this means is for every input value in x, we want to get the model's prediction, and then we put it in a list. So this is list comprehension. Yeah, so let's take a look at what this, let's do some stuff. So given x, a list of input for x, let's say I for I in range 10. So this creates a list ranging from 0 to 9. Let's have y as the output list. So x plus let's introduce some random error for x in x. So yeah, let's take a look at what this looks like. So we have covered data visualization in the previous workshop. So if you're not sure, you can take a look at the past workshop materials. So yeah, so after we have plotted it, we plot show. Let's try using a gradient of 1, a y-intercept of 0. Y hat refers to the list of predictions. Yeah, and let's plot. Run anyway. It's taking some time. Okay, so these are the points that we have generated, the output values that we want to match a best fit line across. And when we look below here, this is the current linear regression model, which we can see it is not fit to the plots that we have created. So right now we want to do perform gradient descent to optimize its cost function and fit it to the best fit line. So let's compute the cost, which is the mean squared error. So let's take the cost as 0 at the start, and then for each value of y minus y hat, we sum the cost. So C, the cost plus, equals to y hat. So the ith y hat minus yi, and then we square it. And then we return 1 over 2 times C over N. So yeah, let's run this and see what it gives us. So this is the current mean squared error of the y hat with the current points. So 0.18 is not the best right now. So here are the equations that we have shown just now. So let us perform gradient descent now. So any questions so far with gradient descent and linear regression before we go into the gradient descent's implementation? Okay. Okay, so let's go into gradient descent. So here we want to use E. E is referring to the number of iterations. M is referring to gradient. C is the y-intercept. A is the learning rate. So this is referring to this L over here. So what we want to do is as we, alright, I forgot. Okay, so so how do we know whether the M and the C values will eventually converge to the optimal values? So imagine a quadratic curve representing the loss. Let's say we are at the left side of the quadratic curve. The gradient is negative. So what does that mean? That means that the current parameter is too low. We want to increase the current parameter. So so the gradient, let's say dm is negative. What we do is this minus sign offsets the negative sign of the gradient and becomes plus. So it increases the value of m. So that is the same for C. So if we are on the right side of the quadratic curve, gradient is positive. And when gradient is positive, this is a minus sign. So C will decrease by some value and will decrease. So when it's on the left side of the quadratic curve, the parameters will increase. And if it's on the right side, the parameters will decrease towards the optima. Okay? Yeah, just let me know if there's no problem and I'll just carry on. Okay, so let's continue with gradient descent. So first, let's generate a prediction of y hat values. Y hat equals to f, x, m, x, and c. So we have defined x just now, m is 1, c is 0. This is what we have initialized our model with. Let's get the length of y hat. So dm, which is the partial derivative, equals to minus 2 over n times, so this is according to the formula up here, minus 2n times sum. So we're going to sum across a list of all the errors. xi times yi minus y hat I for I in range n. Okay, so this is this. So dc equals to minus 2 over n times sum of yi minus y hat I for I in range n. Okay, so this is list comprehension as well, to make the code shorter. So here we have the gradient, we have the parameter updates of m as well as c. So m equals to m minus a times dm. So a is referring to the learning rate, alpha. C equals to c minus a times dc. So let's print the how it changes over time. M equals to, this is f strings, c equals to c to f. So this printing just means that round off to two decimal places. So let us run this. We have the prediction. So we want to run this, and then we want to plot with the new m and the new c, because we have changed the m and c values. I think they are looking at your Telegram. Let me close this. Okay, I close that.
You need to.
I think the notifications keep coming up.
Right. Yeah.
Okay. Alright. So here you can see the linear regression line has improved from as compared to the initial one. So thankfully we can do this with the help of sklearn. Let me just show you this slide. Yep. So this is scikit-learn. This is a machine learning library. yeah, it has a lot of models. There's a lot of functions that you can use for machine learning and certain pre-processing methods. I use it primarily for the pre-processing. Okay, so we use a NumPy array. So this is a list of lists. Why is being represented as this is because each data point may have more than one dimension. So in this case, there's only one dimension. So it's 1, 2, 3, and 4. Let's use the y values of this, which is I just chose this, for convenience. So let's run this. So what we do is from sklearn.linear model. Alright, so yeah, so from sklearn.linear model, import linear regression. We can initialize the model like this, and then what we want to do is we want to fit the model with the data. So what we can do, model.fit x, y, and y equals to model.predict x. So what it does is it fits the data. It finds the optimal parameters, and then we want to predict it given the input values of x. So here, after we have done this, we can look at the coefficients as well as the intercepts, and as well as look at the predictions. Okay, the output is already here. Yeah, and if we plot it, this is the new line. Yep, so you can do this automatically with scikit-learn. Okay, so here we'll be using the California Housing Dataset for today's session. So you can just run the cells by holding Shift Enter. Yeah, it will run. So just run this cell as well, and then I'll move on to the next step. Okay, so right now we'll perform linear regression for the California Housing Dataset. So what we want to do is, given input features, predict the label. So in this case, the label is the price of the house, which is median house value. Is a continuous value. And the input features would be things like longitude, latitude, housing median age, total rooms, total bedrooms, population, households, and so on. And then we want to predict its median house value. So we want to have a y, which gives us all the predictions of its house value. So before we go into that, I need to introduce to you the train test split. So what the train test split is, so we have a lot of data, but we will need to evaluate our model on a set of data to, let's say, measure its accuracy, measure the model's performance in predicting the values. So we can just give all our data as a training data, but then what will we test it on? So we need to split the data set into the training set and the test set. So the train test splits the data set into training and test sets with the purpose of reducing overfitting. So what overfitting means, in the case of linear regression, this is not much of a problem. But for more complex models, say multi-layer perceptron, or I think logistic regression is okay, actually it's a problem for most models. So what is overfitting? And overfitting is a modeling error that occurs when the function is too closely fit to a limited set of data points. So let's say you have a lot of houses. Let's say as x increases, y generally increases, but beyond a certain point, the value of y plateaus. Okay, so if that's the case, a linear model may not be the best case. But let's say we only use a specific subset of the data set, which is at the point when it is increasing. So it seems linear, but then we need to test it on a set of unseen data points to know for sure whether or not it is a good model. So that's why we split into the training and test set. So the purpose of modeling, like a linear model, is to make similar predictions based on the data. the model must generalize to unseen data, not memorizing the training data. So an example would be, say, the tutorials that you do, that would be your training set. Okay, midterms is here. If midterms test you on your homework, you are all going to score very well, which is very good. Yeah, but let's say in the real world there may be more difficult challenges. Are we able to adapt to these new unseen questions, problems? So we must not be memorizing the tutorial answers. We must be able to generalize to the concepts that we have learned. Generalize using the concepts we have learned. So a separate test set with unseen data will evaluate the model well. Yep. So this is the purpose of the train test split. So we'll not go into that in depth into train test split. You just use sklearn's train test split. Yeah, there's an opinion out there that we don't really use sklearn much except for its train test split. Yeah, so train test split is a function that splits arrays and matrices into random, train, and test subsets. So this is how you use it. Let's say X is a series, panda series of its features, and Y is a series of median house value. So when we put into the function train test split like this, this is one line, but I don't have space to fit it in. If we put X and Y here, this is capital Y. And let's say the test size is 0.20. That means that it's going to split 80% as the training set and 20% as the test set. So X train, X test, Y train, Y test. Is this correct? Yeah, so X train, X test, Y train, Y test. So so after you have run this code, this cell, go over here. Let's run this. I'm using random state here so that actually there's no reason why. So after we have obtained X train, X test, Y train, and Y test, let's take a look at the shape of the arrays. So here you can see X train has 16,512 samples, each with 14 features. Y train has 16,512 samples of 1, so this is it's a single value, and your test has 4,128. Yep. So so thankfully we don't have to implement linear regression all by ourselves. We can use sklearn. So we import from sklearn.linear model, import linear regression. Yeah, so linear regression fits a linear model with the coefficients. Can be more than so it can be a multi-variate linear regression model to minimize what is called the residual sum of squares. But you can use mean square error and observe between the observed targets in the dataset and targets predicted by the linear model. So let's try it out. So how we do it? Model. Oh, we did it above, right? Okay, let's do this quickly. Over fit X train, Y train, Y. All right. So if we run this, it will fit according to X train and Y train and predict X test and Y test. Let me close his WhatsApp. How do I close WhatsApp? Okay, so here we have the score, which is referring to the error that it optimized by, which is the residual sum of squares. The coefficient, yeah, these are the 14 features. So each feature has a weight to it. So remember, we have y equals mx plus c. M is one of the weights. Here we have 14 features, so we have 14 weights. The intercept, which is the c, and we have our prediction, which are all of these. So this refers to the house price of the first data point. This is the second prediction and third prediction, and so on. Yep, so this is how you implement linear regression in Python. So I hope that the above implementation from scratch gives you an intuition of how linear regression works and how gradient descent works. So gradient descent is an optimization function that can be used for any model, and it's one of the well-known not any model, but it's one of the more popular optimization methods. There's a lot of others, but gradient descent is one of the fundamental ones. Okay. Yeah. And you have any questions? Okay, let's move on. So now let us use logistic regression for predicting whether a house is expensive. So if it's expensive, return true, or 1, and if it's not expensive, return false or 0. Yeah, so it's the same thing here, but the output is true or false. So what we do is, if it is higher than a certain value, we give them all a label of expensive, and if it's below a certain threshold value, we give it a value of 0. Okay, so what is the difference between logistic regression and linear regression? So for logistic regression, the key difference is this sigmoid function. So what the sigmoid function does is, given x values from negative infinity to positive infinity, map them from 0 to 1. So this is very important because binary values are either 0 or 1, and just now we said that if it's above 0.5, we say that they are all 1, and below 0.5 they are all zeros. So so even though so what we can do for just now that one, given the linear regressor's output of say $100,000, we can put it into this sigmoid function, and then if it's above, it will map it towards 1, and if it's below the threshold, it will map it towards 0. So the good part of logistic regression is that it can output a probability score. So let's say if it's around 0.9, that's 0.9 confident that is 1. If it's 0.2, then it's 0.2 confident that is value of 1. So the sigmoid function is this 1 over 1 plus e to the power of negative x. So this negative x, this is the output from our linear regression model. So this is, you can replace x with mx plus c, and this is the same thing, the same function. So now, how do we know the error? So here we use a trick, which is so y is the label, which can be either 1 or 0, and y hat is the prediction. So when y is 0, this entire term minus y log y hat becomes 0, because 0 times anything is 0. And when y is 0, 1 minus 0 is 1, so it is actually this term only. And when y is 1, when the truth value, the label is 1, this term becomes 0, the right term becomes 0, and this term becomes minus log y hat. So we can sum all of this up, and it will give us the error function of the logistic regression model. So basically, we want to take the prediction minus, okay, I'm not sure why this is here. I think this was from a previous one. So basically, you have a prediction minus a label, and then there's the error. Yeah. So logistic regression is used for classification. Why do we use classification instead of regression? Is to model binary variables, such as predicting whether a patient has cancer or not. Okay, so let's go into logistic regression from scratch. Okay, I hope that this from scratch series is useful to you guys. I slept at 4 AM last night so that you guys have a better intuition of all these algorithms. Okay, so the sigmoid function, we return 1 over 1 plus exponential of minus z. So z is the output, which is from the y equals mx plus c, and then we put it into the sigmoid function. So this is the sigmoid function. So let's take a value from x value of negative 10 to 10. Okay, I saw one of you asked whether you can change the threshold of 0.5 to some other value. Yes, you can. Yeah, you can change the values, the threshold value to suit your needs, but we'll use 0.5 as a for learning purposes. So let's use the value of y. So if we take the inputs of x and we put it into the sigmoid function, this is how it will look like. I'll just run it to make sure that the cell I have the values and the variables. So this is how a sigmoid function looks like, from negative 10 to 10, and when 0 it's 0.5. Okay. Now let's define the loss function. So loss y hat. So n equals, let's take the length of y. So at the start loss is 0. We want to sum all of it. So for I in range n, for each data point, we want to get all the losses. So negative, so this is the, I don't have the equation here. So this is the same loss function as what was shown in the slides. Times math.log y hat I minus 1 minus y I times math.log 1 minus y hat I. And then we return the average of these losses. So let's predict with our sigmoid function. Actually no, let's create some differences. This is not the prediction of any sort. This is just to take a look at how it looks like. The sigmoid x plus, let's use a random, let's use a uniform noise from negative 1 to 1 for x in x. So y hat is noisy and y is the smooth sigmoid function. Then when we run this, this is how it looks like. So the loss function computed is 0.17. Yep. Okay, so basically this is logistic regression. It maps your negative infinity to positive infinity to between 0 and 1. So to do it, we can use sklearn again, thankfully. Okay, there. So from sklearn.linear model, import logistic regression, initialize the model, feed it on the training set, and then predict it on the test set. And then we get the y predict, the y hat. So for the purposes of teaching logistic regression using the housing dataset, we create a new label to represent all house prices above the mean. So our threshold is the mean of the dataset as expensive. So we are predicting whether the house is expensive or not. So note the difference between the classification of binary values, true or false, and the regression of continuous values, which is a range of values. So X is our data frame with the feature list, 14 features, and Y is where your median house value is more than the mean. So this will give us true or false. And then we can use the train test split again from sklearn to get our X train, X test, Y train, and Y test. So let's quickly do this using sklearn. Logistic regression model.fit X train, Y train, and then we predict it. So yeah, so sklearn makes everything really very straightforward. yeah, I failed to converge, but it's okay. So the score here is 0.79, which actually is not very good. I think it's because of the specific data set. Yeah. So to fix this, we can increase the total number of iterations. So how do we increase the number of iterations? So remember just now for gradient descent we use 10 iterations, right? Over here we have with 10 iterations. So we can increase the number of iterations by providing a parameter here, an argument here. Yeah, you can take a look here now. So here we have the tolerance for the stopping criteria. So if the loss is less than, oh wait, no, max iteration. So we have a max iteration over here. So the maximum number of iterations taken for the solvers to converge. So if 100 doesn't work, then we can change to 200 or 300. But I'm not going to do that here because I think it's due to the data set. Okay. So now it is time for k-means clustering. This is unsupervised learning. From a given set of data points of x values, we want to find out which cluster does it belong to. So k-means clustering aims to partition n observations, n data points into k clusters. So k-means clustering, in which each observation belongs to the cluster with the nearest mean. So this I will explain later. Actually, I'll explain now. So each cluster, say I have a cluster over here. All the points that are labeled as this cluster, all those points, their distance to the cluster is the nearest. Okay, I'll explain you the algorithm. So firstly, why clustering? Why perform clustering? Clustering divides the population of data points into a number of groups, such that the data points in the same groups are more similar, such as the t-shirt sizes example. So what we want to do is we want to first randomly initialize k number of centroids. So centroids is just a point to indicate the middle of a cluster. So then assign each data point to the closest centroid. So at the start, the k centroids, let's say 3 centroids. The 3 centroids are everywhere, randomly. We want to assign each data point to the closest centroid. So for each data point, calculate the Euclidean distance to each centroid. And then out of these 3 centroids, assign it to the closest one. So after that, each data point will now be assigned to the closest centroid. So at this point, if you see here at low iteration, right, it's not a very good one. Yeah. And then after that, what we want to do is compute the mean of all the points assigned as each unique centroid. So at the moment, there are this number of points that are assigned to centroid 1. We want to compute the mean of all these points and then reassign that centroid with that computed mean. So for example, let's say we have a set of 5 points here. We calculate the mean of it and then we update the centroid's point as that point. Okay, so let's take a look at the raw implementation for k-means clustering. So first, I'll generate some points. This is, yeah, you can take a look at this. So yeah, I'll be using random state.0, which I'll explain why later. So here we want to create blobs, 20 samples, 20 data points. And then what we want to do is we create a scatter plot, getting all the x values, which is so x is a 2D array where the first column, the 0th column, is the x values, and the 1th column, the first column, is the y values. So we have a list of x values and a list of y values, and when we plot it, it looks like this. So these are the points that we want to perform k-means clustering on. So yeah. So let's use k equals to 3. So the thing is, for k-means clustering, we have to decide how many centroids we want to initialize with. So let's use the centroids. Let's randomly initialize it. So random.uniform. So it looks like it's between 5 and -5. So this will be the x value, and then this will be the y value. Okay, I'm just going to copy these 3 times. So now we have 3 points. This is the first point, the x and y. This is the second point, third point. So we have 3 centroids now. So let's take a look at what it looks like. We want to get the x values of all the centroids and y values of all the centroids, and we label it with red color. So these are the current positions of the centroids. Now we want to assign each data point to the closest centroid. So for each data point, so for example, this data point, it will calculate the distance between this centroid to this, and the distance here, and the third distance. And then because this is the shortest distance, this point will be assigned to this cluster, this centroid. This point will be assigned to this centroid. So this point will be assigned to this centroid. I'm not sure, this one will go here, but this point will go to this centroid. So let's assign each data point to the closest centroid and calculate the Euclidean distance as well. So for each point, x is not referring to the x-axis here, x is referring to the point, so x has x as a x and a y x coordinate and y coordinate. So these are the distances, Euclidean distance. So d distance equals to math.square root. So x0 minus c0 square it. So this is your square root of x1 minus y1 square plus y1 minus y2 square. Yeah. Okay, so x1 minus c1. So this is square. So square the entire thing. So we want to append all the distances to the list of distances, and then we get the distance, we get the index of this. So right now we have 3 distances because we have 3 centroids. So this we have 3 values. So what we want to do is we want to get the index of the smallest distance. So what we can do is list.index mean this. So this will give us the index. So it can either be 0, 1, or 2, as you can see from the output here. We want to put the cluster labels dot append it. And when we print the cluster labels, this is what will be this is what will be shown. So we have the first point being assigned the 0th centroid, the third point assigned the second centroid, and so on. Now we want to compute the mean. So now we have all the points assigned to a particular centroid. So for each centroid, we want to, for each data point in a certain centroid, we want to get the mean of all those points. So I'm going to compute the mean of all points assigned as each unique centroid. So we have new centroids. This will have 3 values. So for I in range k, so for the 3 clusters, so what we want to do is if the cluster labels j, so if the point has a cluster label, so okay, let me rephrase that. So right now, cluster labels, this is the first point, the first point's cluster. So if this is equals to I, so if this is when I is 0 and the cluster label is 0, so if the data point corresponds to that cluster, I want it to append it to data points. So the reason why I do this is so that we can get all the data points and get the average of it, the mean of it. So after this, we can do if the length of data points is equals to 0, then new centroids dot append centroids I. Else, so this is if there are no data points that are assigned to that cluster, that centroid, then we want to just append it. Yeah, and else new C. So this is the new centroid for that particular centroid. Is the sum of data points divided by the length of data points. So new centroids dot append new centroid. So the reason why I can do this is because data points where is it? This x is a numpy array, so you can just do this and you get a new centroid. So if we run this, yeah, so these are our new centroids. So this is the first centroid, this is the second centroid, and this is the third centroid. So there's some change from the previous one. And so let's take a look if we plot them out. So what this is, we want to get the indices of all the points that belong to cluster 0. So we get where the cluster labels is equals to 0, cluster labels equals to 1, and cluster labels equals to 2. And then cluster 1, 2, 3 would be yellow, blue, and green. And then we run this, we give you this plot. Yep, so so you can see that there are some, so the red are the centroids, the new centroids, and the yellow are the data points that are assigned to those centroids. So you can see these 2 points are assigned to this one, all these green points are assigned to this red one, and all these are assigned to the yellow, this centroid. So let us write the above into a function so as to repeat the clustering multiple times. So as this process repeats, the centroids will keep shifting little by little until it reaches the best place that it can be. So k means clustering centroids x. Yeah, let's just run this. So it's just copy paste. So let's perform 10 iterations. So we give in the centroids as well as the data, and it will give us the cluster labels as well as centroids. And we do, after we have done it 10 times, we will plot the same thing again. So here you can see that the clusters are much more, they make much more sense now, right? So they look more isolated and dense to their own cluster. So this is when the points, the centroids have converged to the best positions. So thankfully, again, we have sklearn to do this for us. Can do from sklearn.cluster import k-means. We choose the number of clusters, and then we feed it, and then we predict it. So in this case, notice that there is no y values here, because it is an unsupervised learning algorithm. This y is referring to the cluster labels. So let's run this. Okay, run this again. Yeah, so it gives, so notice, did it change a lot? Oh, it didn't change a lot. So 10 iterations was alright already. Yeah, so our the implementation from scratch was alright. Alright, so these are the three algorithms, three common algorithms in machine learning. So the idea here is that machine learning is not as difficult as you think. There may be some parts that has quite a lot of math, but as you can see, it makes a lot of sense. And to use it, there are a lot of libraries available, such as sklearn. So let me take a look at some of the other models that can be used. So let's see. So clustering, there's a lot of clustering. dbScan. So each of these have their own pros and cons. dbScan does it better for how to say, you have a spread of data which are dense. It can label it as one single cluster. There's agglomerative clustering, which is hierarchical clustering, which is for other reasons lah. So that's clustering. There's a lot of methods here. You can get some data sets from scikit-learn. Yeah, so you have your logistic regression, you have your classifiers, and so on. So yeah, you can use a lot. So you can use a basic neural network here as well. I think it's MLP. So this is you can from scikit-learn.neural network import MLP classifier. So this is a multi-layer perceptron classifier or regressor, whichever you want. So the way you do it is quite straightforward. You can use the, let me see, is that an example? Okay, there's no example here, but yeah, basically scikit-learn tries to make all their designs fit with the training set, test on the predict on the test set. Yep, so this is machine learning algorithms. So we will take a break, and then we will, after the 10 minutes break, I'll pass it on to I'll pass it on to Xingyang to carry on with model evaluation. Yep. Hello. Okay, so for DSC, there is a Hack for Good 2020. So, what is it about? It's a student-run virtual hackathon, unfortunately, to inspire students to learn and use tech for social causes. So, our innovation challenge is unique in that we are posing real-world problem statements provided by non-profit organizations in Singapore. So participating teams are expected to create technological tech prototypes as part of their solution to tackle their chosen statement and directly benefit the NPO backing each statement. So we have environment, equality, and health. So you can look at these three. So we have WWF, Conservation International. So food wastage. What's this? Using tech to create a participatory form of learning in the classroom about the significant role of mangroves in mitigating climate change. How can we assist women to progress in their careers and upskill? People with FCI in Singapore to return to meaningful engagement or employment and community. Tech solution to address issues around stress, anxiety, and depression. And the prize for the champion, Nintendo Switch. Second prize, Kindle Paperwhite. Third prize, Google Home. So come and join. So for our judges, we have a lot of people. So the submission deadline is 17th of March, which is the next Tuesday. So it needs to be based on all the problem statements and submit a presentation deck and so on. So if you're interested, you can definitely go to dsc.com.nus.edu.sg/hackforgood2020. Yeah. So here are our sponsors. Alright. So regarding the project catalyst, so previously we wanted to have a fifth workshop, project catalyst. So the aim of project catalyst is to get people to come together, pitch their personal projects that they find interest in, find out how to craft a data science project, and then look for people to do the project together with. But unfortunately, the idea of this project catalyst is not feasible because of COVID and it being run as a virtual workshop. So there's no in-person pitching of project ideas and so on. So we have decided to remove it. But if you are interested, if you have a data science idea that you are very interested in, feel free to pitch your ideas in the comment section, and hope that someone contacts you and wants to work on a project with you.
this one mute.
On this one.
Desktop now. Yeah, this one then will show. On the second one. You click this one.
Okay. Okay. Hi. So, yeah, we'll continue with the workshop. So after we have tried 3 different models to do classification, regression, and clustering previously, right? So we want to evaluate how well our model does on our data sets. So for usually in machine learning, we have 3 main kind of problems, so regression, classification, and clustering. So I'll be going through some ways to evaluate our models for these 3 kinds of problems. So in this workshop, we use these 3 models for these 3 kinds of problems, but there can be other models that, for example, classification, you can do decision trees or random forests or different algorithms, and these evaluation techniques will still work. So I'll first go through for the regression model. So there will be 2 measures that we'll be looking at today. The first is mean square error. So like Jet previously went through, we have used mean square error as our loss function. So we use this equation to help us to find the line that fits the data the best. So besides that, we can also use this as a measure to tell us how well our model did on the test data. So what we have here is, as you can see, there's this yi hat, right? So what is yi hat? So basically we have all our x variables, our predictors. So like for each of the data points, we have maybe we have 10 features, for example 10 features, so we have 10 x values, right, representing different things. For our housing value data set, those will be like the household income, the longitude, the latitude, things like that. So based on that, we put it so kind of like this line, right? So this is in 2 dimensions lah, but basically we get a y value, which is our predicted value. So usually we use the notation, the hat refers to the predicted value. So yi will be the actual value. So all these y's, right, this n is our test set lah. So basically we are evaluating our model on our test set to see how it performs. So so yi minus yi hat is the actual value minus the predicted value. Then you square it up and you sum it over all the points in the test data set and you get the mean. So that's our first mean square error as an evaluation. And our second is mean absolute error. So the difference is, instead of squaring it, you just don't square it, but you put an absolute function on the value, because if you don't do that, for example, you can see here, right, on the graph, values that are very much higher than the line, like they will kind of cancel out. For example, with this value is below and this is above. So if you don't do an absolute function, they will kind of cancel each other out and you make it seem like error is small, but actually it isn't. It's just one is higher than predicted and one is lower. So these are the 2 functions that we'll use. So maybe we can move on to the code. So basically I have this lin y test as my actual value for the test set, the actual y value for the test set, which is the median housing value. Then lin y predicted is the value that I got from fitting the test predictors into the model, and we get our predicted housing values. So basically what we are using here is from sklearn.matrix, import mean square error and mean absolute error. So yeah, so basically sklearn has this is a library, right? And it has a part of the library is especially for metrics. Yeah, so like there's different metrics for different kind of algorithms. So for regression we have mean square error and mean absolute error. So we just run this function. Yeah. So mean square error is useful for when we are training the model, right? Because it's just commonly used as a loss function. So mean absolute error is more useful, I guess, in terms of evaluating a model, because mean square error, it tells you the error but it's squared, so you can't really determine anything useful. Whereas mean absolute error, it tells you that on average, right, your predicted value is 49,000 off the actual value. So maybe we just run a quick code here, right? np.mean lin y test. So this tells us the average median housing value of the values in the test dataset. So in our test dataset, we have the 4,000 median housing values, right? So yeah, we do np.mean. So it tells you that on average, the housing value of the average housing value is 205,000. Then you have a mean absolute value is almost 50,000. So it means that the value you predict on average will be within like plus minus 50,000 of the actual value, which is like should be 205,000. So I guess this tells you that the model is not doing so well, because 50,000 out of 205,000 is quite a big 25%. So plus minus 25% is not really very good. So I guess this model is not so useful for this problem. But yeah, because we are using a linear relationship. We are assuming that they have a linear relationship, but this might not be the case. So there are limitations to using linear regression for, like, it's not something that it can be used for all kinds of data set. So you can try different other models, which we will not cover. But yeah, basically for regression, when we want to predict a continuous value, we can use metrics like this to evaluate how well the model is doing. Yeah. If there's no other questions, we'll move on to the next one. If there are any, you can leave it in the comment section. So okay, someone asked, can't you just square root the MSE, right? You can't do that, because you have to remember that if you square root this MSE, right, because it's summing over all the values. So if you square root the how do I say? Okay, I guess it's a bit like you are doing a square plus b square plus c square, right? Then if you square root it, you're square rooting the sum of the squared values, versus the second one is kind of like you are doing a mod absolute a plus absolute b plus absolute c. So example is maybe a square, a equals 3, b equals 4, c equals 5. A square plus b square plus c is what? 50. So if you square root that, is square root 50 lah. Whereas if you mod a plus mod b plus mod c is what? 12. Yeah, 12 is not equals to square root 50. This is around 7. Yeah, so there's a difference there lor. Yeah, so that's the difference. Yeah. Yeah, okay. If there's any other questions, you can leave it in the comments. Yeah. Okay. Let's move on to the second model that we talked about, and also the second kind of problems that we usually face in machine learning, which is classification. So in this case, we are using a logistic regression model, as Jack covered earlier. So the most common kind of metric, I guess, it's just accuracy lah. So I guess not even in machine learning, just in many different domains of many different areas of our daily life, right, we will come across like accuracy, right? So obviously accuracy just means the correct stuff divided by everything lah. So correct, right? What's correct? So you can see here that, so we have this table here. So we have stuff that are actually positive, and we predicted it as positive. So we call those true positives. So because we predict it as positive and it's true means like correctly predicted, so it's true positive. Then we have true negatives. So it's actually a negative value and we correctly predicted it as negative, so it's true negative. So false positives, right, it might be a bit confusing, but basically false positives mean the actual value is negative, but we predicted it as positive. So it's kind of like, you can think of it as you are falsely predicting it as positive. Okay, I repeat. So you have falsely predicted the value as positive when it's actually not. So similarly for false negatives, is when you falsely predict a value as negative when it's actually not negative. So our accuracy is true positive plus true negative divided by everything else. That's accuracy. But in accuracy, there's an issue, right? So let's talk about this case study. So in our problem here is we want to diagnose if patients actually have cancer or not. So in this case, our positive class is cancer, because the thing of interest here is cancer. So even though having cancer sounds negative, but here we are using it as a positive class because that's the outcome we are interested in. So so like you can see here, TP equals 0, right? Basically this cell is for when people actually don't have cancer, and we correctly predicted it that they do not have cancer, so that's 0 lah. So for this case study here, we have 30 of the 300 people here actually have cancer. See, 30 actually have cancer lah. Then 270 do not actually have cancer. So 270 of 300 patients do not have cancer, and 30 out of 300 patients have cancer. But sometimes, so we can see that this is actually a very imbalanced class, right? Because only 10% of the data is positive, and 270% of the data is actually a negative. The class is negative lah. So sometimes in our model, it can. I'll not elaborate too much on this, but basically the model will it can sort of take an easy way out, right? If you're using accuracy as a measure to define how successful the model is, because it can simply tell you that it just predicts everything as no cancer. So it just predicts that none of the patient has cancer, and it will still give you a 90% accuracy because there's a lot of true negatives, right? Because true negatives are in our numerator, so it still gives you a very high accuracy, even though this model is actually useless because it's just telling you that everybody doesn't have cancer. But that's easy to say lah. So you just get 90% accuracy even though actually it does nothing. So you can see that accuracy is it doesn't work for cases where the classes are imbalanced, and there are also other areas where accuracy is just not a good measure to tell us how well the model is doing, because most of the time we do not actually care about the true negatives that much, because we just want to know the class of interest. So I want to introduce precision and recall. So what is precision, right? Okay, let's talk about precision first. So basically it's true positives divided by true positives plus false positive. Okay, so what is that, right? So okay, let's look at the denominator here first, right? True positives, basically something is positive and we predict it as positive. That's pretty straightforward. False positive, as I mentioned just now, is when you falsely predict some data point as positive. You falsely predict it as positive. So actually it's negative lah. Okay, so basically the denominator is true positive is what we predict as positive, and false positive is also what we predict as positive. So the denominator is everything that we predict as positives. Okay, if it's a bit confusing, you can ask in the comments. But basically the denominator is everything that we predict as positive. So we want to know, basically it's a ratio out of all the things that we predict as positive, how many of them are actually positive. Okay. So out of all that we predict as positive, how many are actually positive? That's precision. So if our precision is very high, right, for example 0.9, it means that out of maybe we predict 10 positive, 9 of them are actually positive. That's what high precision, what precision means. So in this case, we don't care about the stuff that we predict as negative and are actually negative. Like we don't care about true negatives. That's why it's, remember accuracy, true negatives is in the numerator over everything. Here we don't care about true negatives. So it's just the stuff that we predict as positive. How many of them really are? So what's the benefit of this, right? Basically when the cost of false positives is very high. So example is we are doing an email spam detection, right? So again, the positive class is spam, even though spam is not a positive thing lah. But what is of interest here is spam. So that's our positive class. So what's false positives, right? So false positives is the things that we wrongly predict as positive. So basically they are negative, but we predict them as positive. That's false positive. They are negative and we predict them as positive. So if something is not spam, but we predict it as spam, then it's a false positive. So if our false positive is very high, right, we kind of lose the important emails, because some of the real emails, it gets classified as spam. So we lose our important emails if our false positive is high. So for precision, it takes into account that. So the cost of false positives is high. It says here, we don't really want to have many false positives. It's when we want to improve, when we want to have a good precision. Because when we have a good precision, we won't really lose out on we won't really have a lot of false positives. So we don't really get a lot of things that are spam, they are not spam, that are wrongly identified as spam. Okay, so we'll move to recall. So recall, the difference with precision is again the denominator. So instead of false positives now, we have false negatives. So false negatives are basically positive class that we predict as negative. So positive class that we wrongly predicted it as negative. So basically the denominator is everything that is positive, because false negative are actually positive, right? And true positives are actually positive. So the denominator is everything that is a positive class. So that's why this is a ratio, a proportion of out of all the y values, right? all the oh, okay, I missed a word here. Of all the actual positive y values, how many of them are predicted? Oops. Of all the actual positive y values, how many of them are predicted positive? So if our recall is very high, it means that we are retrieving most of the data we label as positive. We are correctly predicting them as positive. So we use recall when the cost of false negatives is high. So you notice a parallel here, right? Previously, when the cost of false positive is high, we kind of want a good precision. If the cost of false negatives is high, we want a high recall. So for this case, this example here, we do cancer detection or like just in general medical stuff lah. Because basically in these kind of scenarios, our positive class is having a disease, or in this case cancer, because that's what we are interested in. So our positive class is having a cancer, and our false negative will then be cancer that is wrongly identified. So cancer is a positive class, but we identify it as a negative class. When that happens, that's a false negative. So a positive wrongly identified. So a positive identified as a negative, that's false negative. So when you have cancer identified as no cancer, that's a bad thing, because obviously it's a bad thing. You want medical attention fast, right? So in these cases, the cost of false negative is very high. Human lives. So you do not want to have a high false negative. You want to keep it as low as possible, right? So when the false negative is very low, our recall is very high. So for these kind of domains, these kind of areas, right, where they're doing disease detection, things like that, we want a very high recall because we do not want any false negatives. Yeah. Basically, that's recall. So yeah, it might be a bit confusing, but you can take some time to internalize. One is about false positive and one is about false negatives. So yeah, basically this square thing, right? Or we have previously seen it here also. It's called a confusion matrix. Yeah, so it's a confusion matrix where basically we get like four stuff lah. TP, FP, FN, TN. In whatever orientation, it doesn't matter. So using our measures here, right, on the previous data set, on this previous case study here, right, for these values, our accuracy is 90, but actually the recall and precision are both zero. So yeah, why is that? So using precision and recall, compared to our previous conclusion, right, where we only use accuracy, it tells you that it's correct 90% of the time. Basically, it's just saying nobody has cancer, and you'll be right most of the time. But that's not a good conclusion. So our better conclusion here is our precision value of 0, right? It shows that none of the positive predictions are actually positive. That's why it's a 0. The proportion of true positives over the positive predictions is 0. So it shows that none of the predictions are actually positive. The recall is also 0. It shows that none of the positive data classes, right, are actually correctly predicted. It means everybody that has cancer, right, we didn't even predict, not even one of them. That's why it's 0. And actually, from the table previously, you can see it's pretty obvious that because it's predicting that the number of people that they predict have cancer is 0. That's why precision recall are 0. And so the better conclusion is, basically it's this. It says 0 for both precision and recall. It's just predicting that everybody has no cancer. That's why it's not useful at all. So you can see the very different conclusion. Of course, this is a very extreme scenario we won't usually see this kind of such an extreme scenario. But yeah, metrics are important because it can tell you a very different story. Yeah, so previously we thought that 90% of the time is correct, but actually precision and recall tells you that this model is not useful at all. So just now we talked about precision and recall. Then let's consider this another metric called F1 score. So F1 score is a harmonic mean of precision and recall. Basically, it just means the inverse of precision plus the inverse of recall. You can see this 2 over the inverse plus inverse. Or you can also simplify it to 2 times precision times recall divided by precision plus recall. So this F1 score is kind of, it gives weight to both. It kind of is a balance between precision and recall. Because usually when precision is high, recall is low, and vice versa. Yeah. So let us move to the code again. So yeah, we have all these. We can import all these from sklearn.matrix. Accuracy score is accuracy, then precision, recall, F1. So you can run this and it gives you the score. So 0 is the lower bound and 1 is the upper bound. So it tells you 79% of the time the model is accurate. Precision and recall are these values, and F1 score is this. So like you see here, it's not as extreme as the previous example, because there's in this case our clusters are not that imbalanced. That's why you don't see such a big difference. But accuracy, the precision and recall takes into account the false positives and false negatives without caring too much about the true negatives, which we are usually not interested in anyway. Okay, if there are any questions, you can leave it in the comments as well. So we will move on to clustering. So there are different clustering techniques out there. In today's workshop, we talk about k-means clustering, but there are other clustering algorithms out there. But this metric will work too. So basically what we want to do here is, it's called a silhouette coefficient. So this coefficient, right, is of a particular point. Take note of that. So it's of a particular point. So we have this equation here. The mean distance between B is the mean distance between a point and all the other points in the nearest cluster, and A is between all the other points in the same cluster. Then do B minus A divided by this. Okay, so what is this, right? Okay, so for example, our point of interest is this. We are looking at we want to calculate the silhouette coefficient of this blue point here. Okay, so first we want to calculate A. What is A? Right? A is the mean distance between a point and all the other points in the same cluster. So basically you just take the distance lah. Take note that the red points are the centroids. So these centroids are not actually real points. That's why we don't take the distance. These are not actually real points. It's just the mean of the points in the cluster. So we just take a distance between this particular point of interest and all the other blue points. And we get a mean. So basically we add up these 5 distances, and we average it. So that's our value A. Okay, what's our value B, right? So we can see that the green cluster is the nearer cluster. In this case, there are only 3 clusters. So the nearest clusters is either yellow or green. So in this case, we can see it's green. So we just do the same thing as we did previously. Calculate all the distances, then we get a mean. So in real scenarios, right, sometimes the points might be more, you might not know which is the nearest cluster. So we have to do when we write the code, right, we have to calculate the distances between this particular point and the other 2 clusters. And we just take the lower one. So in this case, it's pretty obvious that the yellow cluster is the further cluster. But in the code, we will just compute both of these average values, then we'll take the minimum. Yeah, and that will be our B. So we get our B, our A. You do B minus A divided by the max of A or B. I'll explain why later. So that's our coefficient of a point. Do note it's only 1 point, right? So we repeat the process for all of these 20 points and we get the average. And that's our silhouette score, or you can also call it, I guess, average silhouette coefficient of all the points. Yeah. So just sum out all the values, all the coefficients, and get average, and divided by the total number of points. So that's the score. So this score, the closer it is to 1, the better it is. So what does 1 tell you, right? Okay, so assume that we have this extreme case where the score is equals to 1. Basically, when the score is equals to 1, right, all of these S also has to be equals to 1, right, because they're taking average. So let us look at this. For example, maybe we have a B equals to 1 and A equals to 0. So B equals to 1 and A equals 0, it will give you S equals 1. What does it tell you? So if B is equals to 1, right, it means that the distance between your points and all the other points in the nearest cluster is 1. And A equals 0, it means that every point is exactly on the same point, which is impossible. But example, all the points are on the same point. So that means it's very dense, right? That's why A is 0. And oh yeah, max A of B, it will just return you B. That's why B divided by B is just equals to 1. So it doesn't matter what the value of B is, but if everything is clustered together, A is equals to 0. So this is essentially just B divided by B. That's why it's equals to 1. And if all the points in this data set have this kind of property, right? Yeah, you will just get 1. Basically, in all the clusters, everything is very close to each other. That's why it's highly dense and it's equals to 1. Yeah, so nearer to 1 is very good. Minus 1 is kind of just the opposite. Means the points that are very close to a particular point, right, is labeled as is in a different cluster. That's why the A value is very high. That's why our A value here is very high, because yeah, within the same cluster is very far. But B value is almost close to 0. The distance between this point and some point in another cluster is very close. So that's, yeah, we don't need to go there. It's very weird. So yeah, basically 1 is highly dense. We want to get as close to 1 as possible. So, okay, we have this code here. Basically, this code does the same thing as this sklearn code over here. Yeah, but you can just run this, and it tells you is 0.54. So remember, it's these clusters. These 3 clusters here give us a value of 0.54. So yeah, I guess all these are just values, right? So it's a bit hard to interpret this in terms of absolute values, like what does 0.54 mean actually. But you can use it to compare between different number of clusters. So in our case, we only have 20 samples. That's why it's not very adequate. But for example, if you change the number of clusters, it will give you a different coefficient, and you can kind of use it to compare relatively which number of clusters is better. Like for example, I change it to 4 here, and you will get a different value. Of course, this is you don't really do it like this. There's the kind of thing called validation set, but okay, never mind. So yeah, so it's a bit hard to determine what this pure number means by itself. it just kind of gives you a gauge that the closer it is to 1, the better. So if you compare across different number of validations, different validation sets where the number of clusters are different, and I don't know, there are other things that affect the final performance like initialization and things like that. You can kind of see which one has a higher silhouette coefficient, and that will generally mean that the clustering algorithm is doing better. Yeah, so you all can take a look at this if you're interested. Basically, it's the same, it's how it's implemented here. And yeah, so that's for clustering. Yeah, that's basically how we evaluate our clustering algorithm. There are also different other ways to evaluate, and you can just Google. Actually, it's very easy to find. Yeah, like clustering metric, regression metric, whatever. Or you can take a look at the sklearn.metrics site also if you are interested. Yeah. So you can see here that there are different metrics here lah, but some of them are not really used by people. But you can see like classification metrics, all these, regression, and clustering. Yeah, so these are generally the three kinds of machine learning problems, and there are many more models and algorithms out there, which you all should take a look at if you are very interested. And yeah, so that's the end of our workshop. Yeah, maybe you all can help us fill up our data feedback form. So yeah, hang on.
Hi, so thanks so much for joining us for the workshop for machine learning and analytics. Thanks so much if you have been joining us for the past few workshops. We regret that due to the coronavirus situation, we are not able to provide personalized feedback and guidance for you all. But nonetheless, I hope that you all have learned and took away something from this workshop series on data analytics. Yeah, so here is just a show of the behind the scenes. Yeah, we are all still in School of Computing, so yeah, thank you for your support. Please fill up the feedback form. Otherwise, thank you and see you next time.
Just show you thank you. Okay, 报告。